So we are now on to our very last group of derivatives, which is the rest of the exponential functions as well as the logarithmic functions. So just as a reminder, which I know that we know, the best derivative ever, the derivative with respect to x of e to the x is, of course, e to the x. And so we're going to use that to come up with what all of the other derivatives are for different exponential functions. So like it says there, we've only talked about one specific exponential derivative. And remember, an exponential function is a number raised to a variable. So what we've got coming up right now is the general exponential derivative, so b raised to the x. So 2 to the x, 7 to the x, 4 to the x, something like that. Keep in mind, first of all, those bases can only be positive. So what this derivative is you've got this constant of the natural log of b, and then times b to the x. So every exponential function still has an exponential derivative. It's just going to have some sort of different coefficient out front. And now keep in mind, if we put e in as the base, it still works. So if we did this formula right up above, if we plugged in e right here, we would get the natural log of e and then times e to the x. Of course, the natural log of e is just 1, which is why this comes out to be exactly e to the x. Now, this is something just quick to learn about e. We know that e is approximately 2.718. We also have rational or other irrational numbers like pi, and I know we've talked about this before, but pi actually has a real meaning in geometry. It's the ratio of a circle's circumference to its diameter, and so that's where the irrational number pi comes from. E, the reason that we came up with e, I say we as if I had anything to do with it, the way that mathematicians came up with the number e is because they noticed that all exponential functions had exponential derivatives, so they figured there must have been one exponential function out there that was its own derivative, and that's how they came up with the base of e. Right, so that's exactly what e is in calculus. So now a few examples. Quick derivative here. These are all exponential functions that have different bases. So if you have 3 just to the x, this is just going to be your normal parent function. So this is just the natural log of 3, and then times 3 to the x. Now notice that we keep this coefficient, natural log of 3. It's not a pretty coefficient, but it's still just a constant. We keep that separate from the base of 3 that we're raising to the power of x. These next few require a chain rule. This one we've got 5 raised to the x cubed power, so we still do our outside function. The derivative rule is the natural log of 5, and then times 5 to the x cubed. Remember, you always leave your nested function in place. The nested function stays exactly where it is, and then we multiply by the derivative of the nested function. The derivative of x cubed is 3x squared. All right, so I'm just going to clean that up a little bit. So 3 in the natural log of 5, those kind of end up being our coefficient. It's an ugly coefficient in front of an x squared, and then times the exponential function. So this, for me, since I love to simplify, this is painful to me to look at, but unfortunately it is actually the most simplified that I can make this expression. All right, we've got another one, very similar here. Natural log of 4 to the x. 2 raised to the 4x. I was looking at these natural log functions. 2 raised to the 4x. So we still do our derivative rule. We start with the natural log of 2 because that's the base, and then we keep the 2 to the 4x, but because we have a nested function of 4x, we have to multiply by its derivative. And so we multiply by 4, which is the derivative of 4x. So now let's bring the 4 out front. 4 times the natural log of 2, and then times 2 to the 4x. We could simplify this up if we wanted to. Now notice this, do you guys remember if you've got a constant out in front of a natural log function, you can bring it in as a power, so we can bring 4 in as a power on 2. And so we could do the natural log of 2 to the 4th, which is the natural log of 16. And then you could also, this thing right here, you could do 2 to the 4th to the x, which, just to point out while we're looking at that simplification, first of all, totally fine to leave it like this, totally fine. But if we're looking at this, we could have done 16 to the x right from that point, because we could have taken 2 to the 4th, noticed that it was 16, and then raised that to the x, and just using this basic derivative up here would have taken us right to this point. So just things to simplify. We've talked the last couple of days about making sure that you simplify things if you spot them, because a lot of times it'll make your calculus a lot easier if you simplify first. So we've got one more of these. This is another chain rule one. So your base is 3, and then your nested function is cosine. So we still start with the derivative rule, natural log of 3, because that's our base, and then you just leave the exponential piece exactly the way it is, but then you multiply by the derivative of the nested function. Our nested function is cosine. Its derivative is negative sine. So let's clean that up. So the only thing I would do here is move the negative out front with the natural log. And then times 3 to the cosine x, and times sine x. Again, a little bit painful for me, maybe for some of you, but there's not really anything that we can do to simplify that up. All right, so that's our exponential stuff. It's basically just another rule that you need to memorize. For some reason, people have a really difficult time memorizing this one, so take a careful look at it. So inverses. We've talked about this. We talked about this at the beginning of the year. You learned about it in pre-calc. E to the x and the natural log of x are inverses of each other. So this is why we did the inverse chapter right before we did this, so we could come up with a derivative. So using the inverse derivative formula. So let's actually flip back, because if you remember, we had a sentence that we would use. So this. G prime of whatever is the reciprocal of f prime of whatever, where f of whatever equals 4, or I really should stop saying the word whatever. Let's go back to the generic one. Here it is. G prime of b is the reciprocal of f prime of a, where f of a equals b. Okay, so I'm going to keep this so that I can just flip back and forth. So what we know is that, so let's say that f of x equals e to the x, and g of x equals the natural log of x. So here's what I know. So on my function g, if I plug in x, now we're going to do this generically, we don't want to plug in a specific value or anything. If I plug in x, what I get out as my y value is the natural log of x. So that means on my function f, remember I have those opposite points that I can just flip x and y. That means if I plug natural log of x into my e to the x function, what I get out is just an x, which is true. If I do e to the natural log of x, I just get an x. All right, so I know I've got those opposite points there. All right, so let's take a look at that sentence. Okay, so here's an example. Right there. So g prime of b, which is what we're interested in. We want g prime of x. So g prime of x is the reciprocal of now the opposite, f prime of natural log of x, where f of natural log of x equals x. So that's that sentence that we had on the front. Sorry, that was crooked. So that sentence that we pulled from one of the previous sections. So g prime of x, which is what we're trying to find. We are trying to find the derivative of this function right here. It's the reciprocal of f prime of the natural log of x, where f of the natural log of x is x. So if we want to find f prime of the natural log of x, what we do is we take the derivative of f. So f prime is e to the x. If I want to know the derivative of natural log of x, that means I've got a nested function. So if I want to know the derivative of the natural log of x, what I do is I plug the natural log of x in here, because f prime of x is this, f prime of natural log of x, I want to plug in the natural log of x. So that would be e to the natural log of x, which, since those two are inverses of each other, if I take e and I raise it to the natural log of x, what happens is the natural log of x cancels with e, and then I am left with just an x. All right, so that's this right here. This ended up just giving me an x. And then if I go back to the beginning, g prime of x is the reciprocal of that. So if I just get an x, that means that g prime of x is the reciprocal, which is just 1 over x. So, in conclusion, down here, the derivative of the natural log of x is 1 over x. Okay, so now let me just show you those two functions in a calculator, now that we know what the derivatives look like, so we can compare. So if you guys remember the natural log function, we've got the natural log of x. So let's hold that a little closer. There we go. Okay, so there's our natural log of x function. So a couple things to notice. First of all, it is always increasing, which means its derivative is always going to be positive. Here, it's got an incredibly, incredibly steep derivative. And then it starts to slow down, and by the time we're even approaching 10, the derivative is pretty flat. It's a pretty low value for the slope. And then another thing to point out is that it's only defined for positive values of x, so that's just something to keep in mind when we graph the derivative. So I'm going to hit tab so I can enter in the derivative, which is 1 over x. Okay, so now we're just going to ignore this left-hand side, because remember it's only defined here. So now, like I pointed out, very, very steep derivative here, which is why I'm coming from such high x values. I said that this function is always increasing. Notice that the derivative is always positive. And then as my function starts to slow down, the slope is headed towards 0. All right, and again, we're just ignoring that left piece. So that's the derivative of the natural log of x. So we are going to use that on the next page to simplify up some of these derivatives. Let's look at a few examples. So again, we've got some chain rules, product rules, things like that. So a few examples. If we look at the chain rule, the main function is natural log. The derivative of natural log is 1 over x, but I leave the x squared in place. So 1 over x squared, and then I multiply by the derivative of the nested function. So the derivative of x squared is 2x. And so copy of x will cancel, and I end up with 2 over x, and that is my derivative. One thing I could have done, if we're looking at this right here, always keep in mind that with natural logs you can apply some of these log properties. One of the log properties says that the 2 could have come out front, so I could have written this as 2 times the natural log of x, and so the constant would just kind of hang out front while I take the derivative of natural log of x, which is 1 over x, so I could have gotten right here and kind of skipped the chain rule. Just an option. This one, product rule. I have x squared times the natural log of x. So my first function is an x squared. My second function is the natural log of x. The derivative of the first function is a 2x. And then this brand new derivative that I just learned of the second function, the derivative of natural log is 1 over x. Okay, so I crisscross here. So my product rule is an x squared times 1 over x, and then plus a 2x times the natural log of x. So all I can do here is simplify down a little bit. X squared times 1 over x gives me an x, and then plus 2x times the natural log of x. So that is my simplified derivative. Okay, now this one here, I have kind of a chain rule within a chain rule, I guess. So let's figure out how to simplify that up. So let me switch colors really quickly. So this inside function right here, that will be our u. We can do a u substitution. So if we write u equals the natural log of x cubed, we can come back and do a little bit of work on that in just a second. All right, so let's rewrite this as the natural log of u. So if I'm trying to find the derivative of this, here's what I get. I do 1 over u, because that's the derivative rule, same as 1 over x, except now I have a u in place. But because I have a nested function, u, instead of an x, I have to multiply by u prime. Okay, so now over here, let's figure out exactly what that u prime actually is. So u prime, I do another chain rule here. This is now, my main function is actually a power rule. The 3 comes out front, power drops down to a 2. All the while leaving my nested function exactly where it is. That's the biggest mistake with the product rule, is trying to change the derivative in here instead of multiplying by the derivative later. So then I multiply by the derivative of 1 over x. So now let's plug all this in. So 1 over u. So this is actually, with natural log, we actually do that same power thing like we do with trig. So I'll write that in our final answer here. And then times 3 times the natural log of x, quantity squared, and then times 1 over x. Okay, so let's clean this up a little bit. Here, now there's some canceling that's okay, there's some canceling that's not. Canceling out the 2 common copies of the natural log of x, we can absolutely do that. We can do that. So we've got a 3 is really going to be the only thing in the numerator. We are going to cancel 2 copies of the natural log of x. So I only have a single copy left, and I also have an x. So I'm going to put the x first, so I can write it like that. So that is my derivative all cleaned up. Okay, so now we've got some kind of applied problems here. So now we want to find a tangent line. So to find a tangent line, let's just write this out really quickly just to remind us. So the y value we get by plugging in the x value. We know the x value. So there's that. We don't know the slope. We don't know the y value. So let's get the y value first. We get the y value by plugging in the pi over 4 into our equation right here. So y equals the natural log of the sine of pi over 4. Okay, so the sine of pi over 4 is root 2 over 2. And that is actually really all that we can write for that. Really ugly, but it's about the best we can do. You do not ever want to get a decimal value. You always want to write your exact value. So that's the y value, so you just kind of plug it in, as ugly as it is. And then to get the slope, we take the derivative of this function and then plug in the x value. So y prime equals, so back up here to the original. The main function is natural log, so I do 1 over, and then I leave the sign in place. And then I multiply by the derivative of the nested function. So the derivative of sine is cosine. So I end up with cosine over sine, which I'm hoping we notice is cotangent. Cosine over sine is cotangent. So that's kind of funny. We've got the natural log of sine of x. Its derivative is just a nice, neat cotangent. So what I do to get the slope is I plug in my pi over 4. Cotangent is cosine over sine. If I plug in pi over 4, I get root 2 over 2 over root 2 over 2, which of course reduces down to just 1. So my slope is just a 1. So that is my beautiful tangent line. Remember, no need to simplify beyond that point. Okay, and our last little bit here, a log with another base, because we talked about the natural log, which is log base e, but now let's say we've got another base. So this one, let's calculate just an example here to see if we can come up with a general formula. So if you guys remember this, the change of base formula, log base 8 of x, we had this thing, like I said, called the change of base formula, where you would do the natural log of x over the natural log of 8, and that was so that you were able to plug them into your calculator, because our calculators can't do any other base besides e and 10. So this thing right here is exactly equivalent to this thing right here. So if I want to take the derivative of this, I could just take the derivative of this. Now, one thing I want to point out to you that you guys would try to do, I promise, if you were doing this on your own, you would try to do a quotient rule. But remember, natural log of 8 is just a constant, and so really I have this like 1 over natural log of 8 as a constant, and then I'm taking the derivative of the natural log of x. Okay, so don't forget we've got that constant multiple rule that says it can just come out front. So 1 over the natural log of 8, we just kind of leave that right where it is, and then we multiply by the derivative of natural log of x, which is just a 1 over x. So this is 1 over, the natural log of 8 is, again, just a constant. It's a weird, irrational constant, and I just multiply that by x in the denominator. So my general formula, if I've got some sort of base other than e, it just goes right here. Keep in mind, if that were an e, then it would still be just 1 over x. So my general formula is the derivative, I get 1 over, my coefficient is going to be the natural log of b, which is, again, just a weird, irrational constant, and then times x. So that's my derivative. All right, so we've got this one multiple choice problem right here. This thing, careful, it didn't copy very well. This is supposed to be a plus. You can see it if you look closely. So this is just like a very easy multiple choice problem that I just want to practice now that we know the derivative of natural log of x. So they just want f prime of 1. So we start with f prime, and then we can plug in the 1. So the derivative of 7x is a 7, because it's a linear piece, minus the derivative of 3 is just 0, so you definitely don't need to write that, but you can. And then plus the derivative of natural log of x is just 1 over x. So just a very basic derivative. So they want us to plug in the 1. So really the only place we can plug in the 1 is right here. So I end up with 8. Okay, so that's it for this one. Kind of a short one for you guys.